Welcome, everybody. Glad you could join us for this very first Workshop Wednesday of 2026. Excited that you're here. If you guys haven't participated in one of these programs or seen me before, I'm Dr. John Lohr. I work in the national office with Science Olympiad on projects like this. And I'm excited to offer, I think, a really cool presentation tonight. Erin Barrick is going to talk to you about material science. And as I was talking with Erin, she's been a long time event supervisor for us with this topic area, but she is also a practicing material scientist. So I think she's got some really cool insights and be able to offer you guys a lot. A couple of little things and kind of some business stuff, if you will. If you want to ask questions, please use the question and answer feature. It's in the Zoom toolbar. It's towards the right-hand side, just off of the middle, kind of to the right. It says the little box with the question mark in it, and it says Q&A. I ask you put all your questions there because that way we can track them and we can make sure we get as many questions as we possibly can answered. If you have any issues about things like, hey, I don't know, did the video freeze? Is the sound off? There's a weird echo. Is it me? Is it you guys? Please put that kind of stuff in the chat, and we'll be monitoring both and be able to, kind of inform you guys through both of those. And also, should Erin have anything she asks of you guys, like, you want to share where you're from, what team you're on, that kind of thing, all that kind of stuff goes into the chat. All right. If there aren't any other business stuff, I'm going to turn it over to the reason you're here. Erin, thank you so much for doing this, and please take it away.
All right, thanks, John. Okay, I'm gonna go ahead and share screen. Okay. All right, and then I'm just going to go back to the big. There we go. Okay, perfect. Oh, I'm just trying to make it so that I can see the there we go. Okay, perfect. So now I can see the chat if there are questions. Perfect. Well, hi, everyone. Thanks so much for joining this webinar today. As John said, my name is Erin Barrick, and today I'm going to be talking about material science, and we have this great title, Give Me the Tech, the Nanotech. I was the 2025 National Event Supervisor for the material science event, so maybe some of you who are joining met me at that and did the event, and if so, nice to see you again, and for the rest of you, it's great to meet you all. And I'm also a longtime New York and New Mexico state event supervisor, and I'll explain that split in a little bit. Um, Before I get started, I really wanted to give you a little bit of background and tell you how much I like material science. I'm a proud graduate of Kellenberg Memorial High School from New York. I participated in Science Olympiad there we go. Okay, go back. From 2005 to 2010, and I found this fun picture of myself from 2010 when my team got sixth at states, which was super exciting. And then I moved one state over to Pennsylvania, and that's where I learned about material science. So I went to Lehigh University and I majored in material science and engineering. And so I got a bachelor's, and then I decided that I was loving material science so much that I would stick around for 6 more years to complete the whole decade at Lehigh, and I got a master's and also a PhD in material science. And along the way, I got to do some really cool things in grad school. Like this is a picture of me from 2017 working on an atomic resolution transmission electron microscope. So maybe some of you who have been studying this event now for several months know what a TEM is, and I got to look at columns of atoms on this microscope, which was super cool. And when I graduated, I moved to Albuquerque, New Mexico, which is where I currently reside, and I'm a staff member in the metallurgy and welding engineering department. So I personally specialize in metals and also welding, and so it's been really fun this year to learn about nanomaterials as part of this material science event. And so here are some other fun pictures. This is a picture from 2 years ago at one of my friends' weddings. The five of us here, we were all in Science Olympiad together in high school. And so, maybe you're watching this webinar right now with your rocks and minerals partner or your material science partner. And you know what? Like, you might be at their wedding 13 years from now. So it's a really special organization, Science Olympiad, where it created some lifelong friendships. And here are some fun pictures of material science from last year, where my sister and I had a lot of fun running the puck drop. If you all remember the concrete puck drop, and you competed in that. And also after nationals, we got ourselves some hard-earned ice cream after running the material science event. So it was a really great time. So super thrilled that you're all here for this webinar. Really briefly, just so we all come up to speed, what is the material science event, right? Many of you are probably super familiar with it at this point, but really simply, it's a chemistry event. So we live in under the chemistry committee, and there are two parts to our event. So we've got a written test and a lab activity, and so that's how we've broken up on the rule sheet. And the topics for both the overall topic for both the test and the lab activity is nanomaterials. And so that's our big focus of the year. A little bit different than last year when we did ceramics, but a lot of the information, if you participated last year, a lot of the information is going to carry right over, which is great. So high level, what are we going to do here today? So I thought about a couple of prep tips that I wanted to focus on to help you all succeed in the event. So we're going to go through three like prep tips, I'm calling them. The first two are about how to study for the event and maybe change your mindset a little bit when you're preparing for the event. And then prep tip number three is all about the lab, and I'm going to give some example lab activities that you can practice or you might see. And then save plenty of time for questions. More than happy to answer questions during this presentation. So feel free to put them in the chat, and we'll address them as they come up. Especially if it's something that's just like burning on your mind that's very related to what we're going through. So with that, all right. So the first thing I'm going to suggest for you all as you're prepping for material science is embrace the materials mindset. And what do I mean by that? Well, first of all, I want to talk about a little bit about what material science is. And yes, you probably know what that is by this point. Oh, I see. We already have a question in the chat. I have lots of recommendations for lab activities for nanomaterials. So I'm gonna save that for a little bit and prep tip number three. But if I don't address it, definitely ask it again. So anyway, jumping back into material science overall, it's a interdisciplinary field, right? So we combine a lot of things together. We integrate principles from physics and chemistry and engineering to understand the properties, structure, performance, and behavior of material science across a variety of applications. And you might be laughing that I grabbed this definition from ChatGPT, but I really like it because it does get at the heart of what material science really is. You've probably seen it referred to as material science and engineering. That's actually what my degrees are in. And so we can break that up into two, like material science and materials engineering. So material science is all about investigating the relationships that exist between the structures and properties of materials. And then materials engineering is really like, how do we take those relationships that we understand and design for them, or engineer the structure of a material so that it performs exactly the way that we want it to. And you'll see that there's a reason that I'm harping on this word relationship. Okay, so maybe you've never seen this before, but one of the quintessential things in material science is this materials science tetrahedron. And so it's this four-sided figure, and at the corners, we have words like processing, structure, properties, and performance. And these are things that we care a lot about in material science, right? We care a lot about how we make our material, which is the processing, right? How we make the material. We care a lot about how the internal components of a material are arranged, right? Those electrons, atoms, the molecules. We really care about the properties, right? The traits of the material, right? Does this material behave mechanically? Should I build a bridge out of it? Or does it have certain electrical properties that would make it really good for transistors? And all of this, ultimately, we want to make sure the material is going to perform the way we need it to for a given application. The reason that this is a tetrahedron, right, is you see that all of the different corners are all connected. And this is the crux of material science, that processing of materials is connected to the internal structure of the materials, which ultimately drives what the properties are and the performance, right? These are all related. If we want our material to perform a certain way, then we need to process it a certain way so that it has a structure that we need. And then sitting at the center of this tetrahedron is characterization. And these are the tools that we use to interrogate the structure of the material and figure out what are the properties. Now, why am I harping on this, right? This seems pretty rudimentary. And this is because the main takeaway that I want you to understand when you're studying is that all the topics on the rules, they're connected. We've got structure, we've got properties, we've got characterization. And so if you take the topics from the rules, we can put them on this tetrahedron, and we've got all of them represented here, right? We've got different characterization methods of nanomaterials. We've got different synthesis methods. We have different properties, right? Physical and mechanical properties, optical, thermal, electrical, and magnetic. And this, I feel, is a strong key to studying, which is that once you realize that the topics on the rules are all interconnected, if you study the relationships between the topics on the rules, it'll help you succeed in the event. And I say this because I remember as a Science Olympian, going into our lab on one afternoon and saying, okay, today I'm going to take all the topics in E and I'm going to learn about them, right? And sometimes I wasn't thinking about that. The topics in E might be related to the other topics on the rule sheet. So as you're going through and you're learning about the topics, I want you to think about how they might be connected to the other topics and start developing those relationships between the topics. And I'll get to in a couple slides, but the reason for that is as we get into more difficult competitions, we're going to ask you questions that require your knowledge of those relationships between the different topics. The other part of the materials mindset I want you to take away from this webinar is understanding the classification of materials, because it'll help you to understand how nanomaterials fit into the broader classification of general material science. So, the general principles of how materials are classified is we classify them by two ways: chemical makeup and atomic structure. And so, based on that, we end up with three primary classes of materials. So, we end up with metals, ceramics, and polymers. And the thing that makes each class different from each other is they have different chemical makeup. So, metals, for example, they're made up of one or more metallic elements, whereas ceramics are compounds between metallic and non-metallic elements, and polymers are all non-metallic elements. And then they have differences in their atomic structure, so how those atoms are arranged at the atomic level, right? So metals have metallic bonding, ceramics have ionic and mixed ionic and covalent bonding, and polymers have covalent bonding. So based on these differentiating features, we end up with three distinct classes of materials: metals, ceramics, polymers. We have this fourth class, composites, which is basically we take two or more of these individual categories and put them together. Okay, you're like, Erin, you've forgotten nanomaterials. Why don't you have nanomaterials on this slide? And I don't have nanomaterials on here because they are a little bit different. Unlike those four main classes of materials, which are distinguished based on their chemistry and structure, Nanomaterials are distinguished based on their size. And so the word nano, that means 1 billionth. So super small, right? 1 nanometer is 1 billionth of a meter, and there are 1 billion nanometers in 1 meter. So, I mean, we can't even see this. To give you an idea of just how small this is, right? Like the average diameter of a human hair is less than a millimeter, it's about 70 microns. So that would be 70,000 nanometers. So there's 70,000 nanometers in one strand of your human hair, which is kind of mind-blowing, right? And so when we go ahead and really define nanomaterials, these are materials where the sizes of the individual building blocks are less than 100 nanometers, at least in one dimension. So these are really, really, really tiny materials. So how can we combine the four classes of materials that I talked about previously with this idea of nanomaterials? Well, we can have all four classes of materials can also be classified as nanomaterials when they are nano-sized. So we have metal nanomaterials, we have ceramic nanomaterials, polymer nanomaterials. And so we have some different examples, right? Like nanomaterials, we have gold nanoparticles, silver nanowires. For our ceramic and semiconductor nanomaterials. We might have silica nanowires and cadmium sulfide quantum dots. And all of the information about the chemistry and the atomic structure still applies. So metal nanomaterials are going to have metallic bonding. Ceramic nanomaterials have ionic and covalent bonding. We are excluding polymer nanomaterials from the topics just to keep the topics list manageable for this year. We did include carbon nanomaterials, which would sort of fall into this category, like carbon nanotubes and fullerenes and graphene. And then when it comes to composites, the way I like to think about it is in actual application, nanomaterials are often combined with bulk materials to enhance or change the properties of those bulk materials. So, for instance, you might put a nanofilm coating on glass to make anti-reflective glass. So that's an example of putting a nanofilm onto a bulk material. And what makes nanomaterials so special and unique is that their properties depend on their size in this nanoscale range, right? So the properties of the bulk material may be different than its nanomaterial counterpart. And of course, like some forces are going to be different at the nanoscale, right? So like gravity is a weak force. So the reason that I went through in great detail, right, like these different categories of materials, is that I think it'll help you to understand the different types of nanomaterials once you realize that they fit into the broader categories of the materials, and then they're just nano sized. So to wrap up this prep tip number one, I'm going to go back to this idea of the tetrahedron, right? Where processing, structure, properties, and performance are all interrelated. And suggest that when I write tests as an event supervisor, typically, when we're at, say, like the regionals level, you know, we might ask simpler questions based on like understanding of concepts, defining terminology, simple calculations. And then, of course, as we progress through the competition season, we start to ask more complicated questions where we really want to understand the applications of concepts, the relationships between concepts, more calculations. I think calculated calculations should be complicated calculations, but they could also be calculated. And so really, as you progress through the competition season, think more and more and more about how the different topics on the rule sheet are related. And I'll give you just a couple of examples um, of some kind of simple, challenging, and more challenging questions where we start to combine the topics a little bit more. So for instance, right, here's a couple synthesis questions. So this might be a simple question where you just have to understand a concept. Which of the following synthesis techniques is considered top down? Right? Anyone want to put their answer in the chat? Yeah, good job. Excellent. Yes, C is the correct answer, milling, right? And so that's like us, understanding concept question, right? Now we can get a little more complicated, right? Describe the process of synthesizing nanoparticles using the sol gel fabrication technique. So now I need to understand a little bit more about how this process works. And then finally, like the most challenging might be what are the advantages and disadvantages of synthesizing nanoparticles utilizing the sol gel fabrication technique with respect to particle size, particle stability, and optical transparency? So now you see that we are combining different topics on the rules because now you have to understand optical properties and synthesis. So you see how we're putting it all together. Some other examples with quantum dots, and this is all since this is being recorded, you can come back to these questions, but simple. Name two common materials used to fabricate semiconductor quantum dots. Challenging. What role does quantum confinement play in determining the properties of quantum dots? And then more challenging, again, combining those different topics on the rule sheets. How does temperature affect the optical properties of semiconductor quantum dots? And last but not least, on carbon nanotubes, right? What is a carbon nanotube and how is it structurally related to graphene? More challenging is describe how defects or impurities affect the electrical conductivity of carbon nanotubes. That actually combines three topics on the rule sheets, right? Defects, carbon nanotubes, and electrical conductivity. And then more challenging, using graphene's band structure, explain the origin of metallic and semiconducting behavior in carbon nanotubes. So these are the types of connections that you'll want to be thinking about as you're studying. Are there any questions on embracing the materials mindset?
No, you're looking good,
All
Erin. It
right.
seems just the one about the lab activities so far.
All right, perfect. We'll keep rolling. All right, prep tip number two. And this prep tip's a pretty simple one, I would think. But as I will say, as someone who doesn't live in the nanomaterials world on a daily basis, when I was getting into this event this year, I realized I was struggling with the terminology a little bit. So on our rules sheet, of course, we refer to everything by nanomaterials, but you've probably figured out by now that there's like all sorts of these other nano terms that are out in the world. And so I wanted to take some time today and clear the air on what all of these terms mean. And so we'll start with nanomaterials, right? These are, as we've just described, materials at the nanoscale, where we've got dimensions, one dimension that's less than 100 nanometers. You've probably also heard of nanoparticles, and this is a specific subcategory of nanomaterials. And I'm actually going to define that on the next slide. Then we've got this big word, right? Nanotechnology. And this is the broader field that encompasses the study and application of these materials. So nanotechnology includes nanomaterials, but it also includes like applications where we're using nanomaterials in real life. And then finally, nanochemistry. And this is like specifically focused on the chemical aspects of nanomaterials and their interactions. Now, why did I go through and define these four different nanoterms? Well, what I have learned as I've been going through different resources to find information is that you'll find more resources and a greater range of resources if you're using all of these different terms as keywords for searches. So you might find different things for nanotechnology than if you were just searching for nanomaterials. You might find more lab activities if you search for nanochemistry than if you just search for nanomaterials. So definitely broaden your search terms. Also, if you like books, right? If you like to study for Science Olympiad with books, I've found the nanotechnology books tend to be a little more easier to digest, especially as you're learning the field. Some of the nanomaterials books, they get pretty dense pretty fast. So again, kind of keep an open mind as you're looking for different resources to study. A few more nano terms, right? And so especially as you're studying for the event, you really want to nail down these nano terms because, um, those of us who are writing tests, we're going to write questions that might ask you about nanoparticles or nanorods or nanofilms, and you want to understand exactly what we're asking about so that you can answer the question correctly, right? So, nanoparticles, these are like somewhat self-explanatory, right? But this is any particle with a diameter ranging from 1 to 100 nanometers. And this includes like irregularly shaped particles. We've got nanowires, which are wires that have a diameter of less than 100 nanometers. And so one thing that you'll notice about all of these is that there's always a dimension that's less than 100 nanometers, but the thing you'll want to keep track of is what is that dimension, right? So for the wire, it's the wire diameter. For a nanotube, it's the diameter of your hollow cylinder. If you've got a nanorod, that's a solid cylinder. So I think you can see where I'm going with this, right? Finally, we've got some nanofilms, some thin films, nanofluids, right? That's where we've got nanoparticles dispersed in a fluid. And finally, we've got quantum dots, where we've broken the trend of nano, and these are semiconductor nanoparticles. And so I included this schematic here, right, about how nanomaterials are classified based on their dimensionality. And so we can see that nanoparticles are zero-dimensional. Nanomaterials, nanotubes, wires, and rods are one-dimensional, and then thin films are two-dimensional nanomaterials. Let's see, we've got a great question about do we have any resources that are video based? I'll be honest, actually, I don't have any of those prepared. I think there's tons of great YouTube videos. If you go on YouTube and you put in specific topics from the rule sheet, that would be where I would go for some video resources. Cool. So that actually brings me to the end of prep tip number 2 about learning the lingo. Anyone have any questions about the nanomaterial lingo? If not, I'll get to prep tip number 3, which is all about the lab, which is what I'm sure you are all anxiously waiting for. So, lab time. All right. So, um, first of all, right, just a refresher on the lab activity. And so, based on the rules this year, at least one lab activity must be performed. So, we've been recommending to everyone to always run a lab activity. And we've sort of like tiered the scoring of the lab. So at the regional level, the lab activities will comprise at least 15% of the total event. And then that goes up, right? 25% and then 35%. So as you work your way through the competition season, you can expect to see more lab activities. And one place to start is we have assembled this chemistry expectations list, and this is posted on the national website. And this gives you an idea of the types of activities that we expect the students to be familiar with, right? So, for instance, we expect that you will know how to light a match, candle, and a Bunsen burner. So I interpret it as be comfortable working with flames. Um, how to use standard chemistry, instruments, know how to take measurements, and work with the proper glassware. And so, first of all, when you're preparing for the lab, if I were you, this is the first place I would start and make sure that I'm at least comfortable doing all of these things on the list. I do see that we have a question about recommended nanotechnology books, and I'll answer that question at the end. My books are sitting behind me and I can pull all of them up. So we'll go through the lab and then I'll make a note that we'll get back to some nano books. I can tell you which ones that I like. Okay. So we'll keep going with lab. Okay. So this is Erin's interpretation of types of lab activities that you might see. And actually, before I get into that, I see there's a question about are lab materials provided or do we need to bring them? So I'm going to answer that question. Uh, it's both. So in the rules, there is a chemistry box, and it's on page like 72 of the lab manual. And the in that it is expected that students will bring that chemistry box with them to material science, and it includes things like a ruler, calipers, like beakers, basically like kind of like standard equipment. And so the students do need to bring the chem box with them. Now, any other equipment that isn't in that box or that's specific to the lab activity that we're going to be doing, you we will provide as the supervisors. And actually, yeah, we will provide as the supervisors. So, going back to Erin's interpretation of three types of lab activities you might see. So, this is just my interpretation of this, but first off, I think that we will see the first one could be synthesis of actual nanomaterials. The second one could be experiments involving actual nanomaterials. The third could be experiments not involving actual nanomaterials, but rather surrogate materials that exhibit similar behavior to nanomaterials. So, of course, like the gold standard would be for every lab activity that you do in Science Olympiad this year to involve actual nanomaterials. But sometimes that's just not practical, right? Some nanomaterials are hazardous, some nanomaterials might be expensive. And so sometimes you might have to do experiments that don't have real nanomaterials, but we will ask you to apply that back to nanomaterials. So, the other thing I want to point out before jumping into some lab examples is we have a new resource guide listed on the national website. So, it's this 26 material science web resources. And when you open it up, it's a document. The first half of the page is good, just like general nano resources. And then the bottom half of the page, there's something like 12 to 15 different resources for the lab. So many of them contain like actual experiments that you can perform as you're prepping for the event. I see we have another question related to lab. I know how last year's lab is creating a puck, but this year, are we needing something beforehand and test it? And the answer is no. This year, there is no bringing anything to the event. So this year's event is just a written test and a lab activity. And so the way I interpret that as an event supervisor means that I can create a little bit more of a substantial lab because there's more time during the event since I don't have the puck drop. So nothing beforehand this year. Everything's going to happen in the event. But as we'll talk about next, I absolutely recommend that you practice, practice, practice lots of labs before getting to the event. So, um, I went through and based on these three different types of lab activities you might see, I came up with some example labs that you might want to practice. And pretty much all of these are listed on that resource guide that I mentioned on the website. So for instance, one thing that's really, really cool for synthesis of actual nanomaterials is you can synthesize carbon quantum dots from kitchen compounds like water, baking soda, cane sugar, and white vinegar. And so these are some examples. Again, these are posted in that list of resources on exactly how to do this. And so this might be something that the students are asked to do during the event, right? Synthesize these nanomaterials. And one thing, if you've done a material science test before, when I'm writing a lab event as a supervisor, usually I write the lab activity, that's what, the students are actually going to be doing. And then there's always questions that follow, and there's analysis questions, right? Think basically getting you to think about the activity that you just did or the experiments that you just performed. So for each example I've given here on an actual experiment, I put some examples of what topics on the rule sheet this is connected to. So for instance, if we have you go ahead and synthesize these carbon quantum dots, maybe we're going to ask you questions about how you synthesized it, like what methodology would this be considered? We might then ask you to use a UV light and demonstrate the fluorescence of these carbon quantum dots, right? Maybe we'll give you some example pictures from characterization techniques related to these quantum dots, right? So as you are thinking about these different, as you are practicing these lab activities, take some time and think about what topics you could connect this to on the rule sheet. I see we have a question, where are the lab examples located? And so it's in this document that says 26 Material Science Web Resources. So I just pulled this yesterday, so hopefully it is still located there. Okay. Another great example of synthesizing actual nanomaterials is magnetic ferrofluid. So this is super fun nanofluid that shows these really interesting magnetic properties. And so there's actually two different methodologies posted in that resource guide. One of them's like pretty involved, involves like some nastier chemicals like hydrochloric acid, ammonia, ferric chloride. And so of course, one caveat I throw out is always follow the directions really carefully, perform synthesis experiments while being supervised by an adult, and thoroughly read through the instructions to make sure that there isn't going to be anything hazardous, or if there is, you're wearing proper PPE. So just if you're synthesizing nanomaterials or working with them, make sure you're being really, really, really careful. But again, we can connect synthesizing of actual magnetic ferrofluid back to topics like magnetic fields, types of magnetism in nanomaterials, surface tension. So these, again, are the types of questions that you might come across after you're doing this lab activity. You can make a simpler version of ferrofluid too. This one's really easy with iron filings, like from the hardware store, and vegetable oil. And it's not truly nano, right? Because like some of the filings are going to be larger. But this is a really like easy way to learn about the ferrofluid. So that was kind of lab category number one, right? Synthesis of actual nanomaterials. What about other experiments that we could do involving actual nanomaterials? So, like we as the supervisors might ask you to work with some nanomaterials. So, two examples here that are super fun. One of them is like nanotechnology stain resistant solutions or fabric. So, for instance, there's this trademarked brand of clothing called Nanotech's clothing. And basically, its claim to fame is that it is stain resistant because when you drop a liquid on it, the liquid is basically going to bead up and it's not going to soak into the material. And the way this works is that the fabric is impregnated with nanoparticles. And so it makes it hydrophobic. So that's a word we can connect it back to on the rules topic, right? And so that's how it's stain resistant fabric. Magic sand is like very similar. It's this really cool sand that's coated with a nano layer of silicone film. So like a nano thin film. And then it's the same thing where the water behaves and balls up on the surface. And basically the sand doesn't get wet. And so these are two examples where we could ask questions about like surface energy, right? Like what are the nanomaterials doing to the surfaces of these bulk materials, right? Wetting angle. What is the wetting angle of these drops of water on the material? The material's behaving hydrophobic. So these are some fun examples. You can find some nano sprays on Amazon. And I'm also going to give you an example in a couple of slides of some non-nano materials that behave similarly that are really easy to get your hands on. Um, Another example of like experiments that might involve actual nanomaterials, maybe we'd give you some pre-synthesized nanofluids, right? Instead of synthesizing the carbon quantum dots during the lab, we could give you some synthesized ones already, and we could have you work with those nanofluids. For example, this is an example of passing a laser beam through, this is actually colloidal silver. And you can observe the Tyndall effect of the laser because this is a colloidal solution or a colloidal suspension, rather. You can actually see the laser beam going through it. So we could ask questions about the optical properties of these pre-synthesized nanofluids. Or if we gave you the magnetic ferrofluid, we could do a lot of the same types of questions with magnetic behavior. We could think about nanofilms on bulk materials. I learned just last week that a really interesting use of nanomaterials is titanium dioxide nanofilms on glass to make self-cleaning windows. I don't know if we could get a window in a lab, but maybe we could get some small pieces. Or, for example, anti-reflective like nanofilm coatings on glass. So perhaps even your glasses that you're wearing have a nano anti-reflective coating. So maybe we could look at the optical properties like reflection and refraction of those. So these are some different ways of like working with nanomaterials, and we could ask questions, ask you to really think about how these different applications are working. I see we have a question in the chat on where can we buy nanofluids? I actually just Googled magnetic ferrofluid yesterday, and there's like a bunch of different places that popped up just by Googling. I don't have like a one-stop shop, perhaps. I think like Flynn Scientific has some options, maybe even Amazon. I don't have a great one-stop solution aside from just start Googling, but they are out there. Great. So the last category of lab topics is the one where surrogate materials experiments. So this is where we don't actually have like actual nanomaterials, but we have materials that are going to behave in very similar ways. So for example, on two slides earlier, I showed that really cool nano clothing and the nano stain protector. Well, there are many naturally occurring vegetables and leaves that also show this same kind of hydrophobic behavior. So this is called the lotus effect. You can see this on lotus leaves, broccoli, cabbage, right? So, and this lesson is posted in that resource guide, and it's really great. And so you can, with just some easy to find grocery items, take a look at these surface tension, wetting angle, hydrophobic, nanoscale surfaces topics, right? And that's one example. Another one I showed on a couple slides earlier, the Tyndall effect with silver nanoparticles, but you could do this just as easily looking at milk versus water, right? So milk is a colloidal suspension, just like a nanofluid is, and so it's the same thing when you pass a laser through it. You can see the laser in the colloidal suspension of milk, as opposed to you can't see it with the water. So that's another example of like a surrogate materials experiment. And so, as you're thinking about these surrogate materials experiments, right? Like when I write a test, if I'm using something as a surrogate, I always ask questions about if this were an actual nanomaterial, how might this be similar or how might this be different? And so what I think would be really fun as you're preparing for the event is challenge yourself. Can you come up with your own surrogate experiments and demonstrations for all the topics on the rules? I think if you came up with that and you thought about how they're connected to all the topics, I think you'd be extremely successful in the event. And so this is my basic second to last slide. I'm gonna leave you with a couple of tips during the lab event, based on some things that I saw last year. So, first of all, read the lab and then read it again. So, when I write tests, I always provide really thorough instructions on how to complete the lab, right? Because I want to make sure that you're going to complete the lab in a safe way and that you're going to be successful. So, read the instructions. I can't stress that enough. And read all of the instructions before you do the lab, right? Sometimes if you don't read ahead, and you make a mistake, you might not be able to go back. And then, as I said, there's always going to be questions after the lab that ask you to analyze what you did during the lab. Read those questions before you do the lab so that you're thinking about them while you're doing the lab, right? So just really read ahead and save time for the analysis and the lab questions. In my experience from running this event last year, the analysis of the lab was where teams struggled the most, right? Most teams were able to do the lab and complete the lab, but the analysis is where people get a little bit tripped up. And so, things that we might ask of you after the lab might be to do some calculations based on collected data. Maybe do some critical thinking about what actually occurred during the lab. Did the lab go the way you wanted it to? Did things come out correctly? Maybe should it have gone in a different way, right? And then especially if we didn't use a nanomaterial, or even if we did, like connecting the lab to an actual nanomaterials application, right? Like, why might you want nanoparticle um, clothing to be stain resistant, right? Like, why is that relevant for us out in the real world? And last but not least, have a strategy for how the two team members are going to tackle the lab, right? And this was one thing I thought was interesting watching last year, that like different teams had different strategies. Some teams, one person worked on the lab. Some teams, um, both partners worked on the lab. And I don't really think there's a best strategy. I think it's whatever you and your partner have practiced and what works well for you. And really, I'd recommend practice both and have a strategy for different lab activity formats. So sometimes when I write the event, I have enough lab setups that each team can have their own lab setup and they can spend the entire event working on the lab. Sometimes it uses really specialized equipment and we have to do stations. And so you don't have as much time working on the lab. So just be prepared for the idea that the lab might vary depending on the competition, and maybe have a strategy for that. Maybe if the lab's going to be a little shorter and stations, maybe both team members work on it to be as effective as possible, versus if you have the whole 50 minutes, then maybe one person can work on it. So think about that with your partner as you're studying for your event. So the very last thing I wanted to leave you with is that I'll kind of go full circle, and the beginning of the talk I told you that like I love materials and they're all around you everywhere. And so, as you're studying and preparing for the competitions, like embrace the fun of learning how innovations in materials have enabled modern technologies, right? There's tons of materials technology in your phone, plenty of nanomaterials in there too. If you really love this event, um, you could you could have a career in it, right? Like you could major in material science and engineering in college, and then go on to become a material scientist. And it's a super rewarding career. Small plug here, like one of the material science professional societies has these camps over the summer. And so students, they have student camps, and teachers, they have teacher camps. And so they are super cool. I used to volunteer at one of the student camps, and they are really, really fun. And so if you're like absolutely loving this event, then absolutely look into some of the camps. They usually are free, which is very cool. And so with that, like good luck with the season, and like I will now answer some more of the questions. Let's see. So first of all, I'm going to show some books. I'm going to grab a few.
All right, everybody. While Erin grabs the books, I just want to quick plug in the chat. I've put the link to the material science event page. That's where you can find a lot of the resources on the Science Olympiad website. Also, if you like this workshop or you want to attend, we have a couple more workshops this season. We got astronomy next week. We're doing disease detectives, anatomy and physiology, code busters. The link to sign up for the workshops is in the chat, as well as the link to our YouTube channel where you can see all the past webinars as well as all future webinars. That's where we're going to post the recordings. So that information is available to you and you want to grab the links. And I'll turn it back to Erin.
Okay. All right. So, this is just my personal recommendation of books that I've been evaluating. So, first of all, this is a very old version, but this is, ooh, can we see that? Yep. This is Fundamentals of Material Science and Engineering by William Callister. And there we go. And this is a classic material science textbook. There's like this is the third edition. They're like up to the eighth now. So there are many, many, many editions of this. You can find old editions online. They're really cheap. This is like everyone uses this in their first material science class in college. And so it is great for all of the fundamentals. It does not have a ton of nanomaterials information. So this is great for like if you want to learn what like crystal structure means or what mechanical properties mean. This is really good for that intro knowledge. I would suggest learning everything from that intro level and then go figure out how it applies to nanomaterials. Okay, some easy nanotechnology books. Okay, this one's really silly, but Nanotechnology for Dummies. It's a good intro book. It's got a lot of really good basic information, and so it is it's good if you have no if you're starting from scratch. It also has tons of applications, which I really like. I've also been looking at this one, this Nanotechnology Demystified. So this one's interesting too. Also very approachable and easy to understand. And then, like I said, some of the nanomaterials ones, they get kind of dense. So then I have this one, this nanostructures and nanomaterials. And it gets pretty heavy. So, take that with a grain of salt. So there's some of the books. There's some others you can find like PDF copies of, which is really nice. So, there's certainly a lot out there. Just bear in mind that some of them get really challenging. Let's see. Got some other questions. So when studying, if I have a question during studying or have something I don't understand, what can I do? Oh, it's quite an open-ended question. You could try looking it up. I will say ChatGPT does have a very good knowledge on nanomaterials. So I have been using ChatGPT to help myself learn as well. So I would use AI to help you learn. There's a lot of nanomaterials knowledge out there, and so using it is a good way to learn a little bit more.
Yeah, and Erin, if I can add, because I was going to suggest the chat option is a great way to at least like it gives you a great summary and it gives you a great place to start and kind of break things down. Um, two tips I'll throw out there about using it. One, don't forget you can ask it to take on or to give an answer in a particular persona. And by that, I mean, in your thing is like, okay, can you explain nanorods to me as if I was a fifth grader or as if I understand nothing about chemistry, right? And you can put parameters in your request and the chat will and the AI, right, will try and do its best to match those things. The other thing I've found that is quite useful is when you get something, because we've all heard the horror stories, right? That the AI gets stuff wrong or it just makes up stuff to make you feel better or to complete the task. The one of the practices I've done is take what the first one gives you and then either put it back in and go, hey, could you check this for any errors and correct anything that's wrong? Or use Chat GPT and then take it over to like Google Genesis or Claude or another AI system and go, hey, again, could you check this for errors for me? Is a way that maybe a step to kind of help you and at least get you over that initial kind of being stuck.
I love that. Yeah, that's like such great advice. Uh, okay, next question. Might we see general material science questions, i.e., ones not necessarily related to nanomaterials, but are still good to know? I would say yeah, because you know, we might ask a, we might, someone put stress strain in a question earlier, right? Like we might say, we might ask a question that says, what is the definition of strain? And that's not necessarily specific to nanomaterials. That's specific to all of materials, right? It's super general. So absolutely, I would say we'd see general materials questions. And that's where, perhaps you put this in before I showed the book, but that's where I would say this Callister book is absolutely dynamite for that general material science knowledge. So that's Callistr, William Callister. And there's a couple different versions, but you won't go wrong with any of them. Let's see. The next question is about the Scioli wiki page. Are there any other resources recommended? The wiki page is super confusing. Oh, it's good to know. I don't know who wrote the wiki page, but I would check out on the national website on soink.org. We have that list of material science resources, and the first like eight at the top of the page are general material science resources. So they're like general nanomaterials websites. And so I would say check those out. The chemistry committee, worked hard to curate those resources. So they should be pretty helpful for you. And then let's see. The next question is definitely a really, oh, sweet. Thanks, John, for putting that link in. Perfect. Um, the next question, this is a really good one. How deep would you say the event knowledge goes? Is the info on a introductory college chemistry level, or does the event require more advanced knowledge? So it's kind of tricky, right? Because like most high schools don't teach material science, and a lot of chemistry curricula don't include material science. So I would say like it's probably a little bit more advanced and would be like an introductory like college level for material science, just because this type of information isn't usually like included in a high school curriculum. But we try to keep it like pretty introductory college level, right? We don't want to go too deep in that sense. Let's see. Got another question that has a puck drop. There's no puck drop this year. Yep. So we're just basically you just need to study and practice for the lab. Uh, we've got another question about when making a cheat sheet, what are some key factors to include? Oh, great question. Okay. So for the cheat sheet, I would for one, include equations. We do have some math in this event. There are some topics on here which are math related, right? Like especially some of the mechanical properties, electrical properties, thermal properties. Those are all those we can ask calculation questions. So for sure have equations and units, right? There's like a lot of different units to keep track of. So I would for sure put units. Um, let's see. I would try to memorize like what all the topics mean, right? So that you don't have to waste room on your cheat sheet with like definitions. I've seen some cheat sheets that are big like walls of text. And so the more that you can memorize, like the more that you can save room on your sheet for things that are like harder to understand. Um, let's see. Someone else asked about main equations we should know. It says, what main equations should we know besides Young's modulus, Bragg's law, Snell's law? Those three are perfect. So we should definitely know Young's modulus, Bragg's law, Snell's law. There are some equations for electrical conductivity. There are some equations for thermal conductivity. Density, I mean, that's an easy one, but like that's an equation to know. I have my rule sheet here in case I'm forgetting any. There's besides Young's modulus, also in the chemistry of surfaces section for like wetting angle, there are some equations for wetting angle. It's also Young's, so it's Young's equation. That's another one that's important. Let's see. Um, if I think of any other equations, but those are the main ones. Will we see questions about the differences of bulk materials compared to the nanomaterials and the different properties involved? I would definitely err on the side of being prepared for that because if someone's chosen to use a nanomaterial, it's because it has different properties than a bulk material, right? And it's giving you some huge advantage over a bulk material. So I would certainly, one of the easiest ones is to understand how the melting temperature changes. For instance, like the melting temperature decreases as you go to a nanomaterial as compared to a bulk material. So I would understand those relationships. And again, think about it like at the regional level, maybe we think about easier relationships and then get a little bit more complicated as we move through the competition season. Um, okay, next question. Can we expect to have to know how to derive specific equations in higher level competitions? Been asked to derive Hooke's law in an invitational. Interesting. Every supervisor's a little bit different. Um, I don't typically ask that kind of stuff, but that doesn't mean that other people don't, right? And so um I guess be prepared for it for to some extent for some of the major equations. Next question, besides equations, are there diagrams or images I should include on my cheat sheet? That's a Absolutely. If there are certain diagrams that you're having trouble memorizing, maybe for sure, put it on the rule sheet. Um, the not the rule sheet, the cheat sheet, right? I mean, the cheat sheet, it's really for you. It's whatever you feel like you can't remember in the moment at the event, or isn't like of best use of your time to memorize. So if I mean, there's plenty of different diagrams you can include. Like someone mentioned a stress strain diagram, right? That's like pretty quintessential. Um, so it's really up to you. Let's see. Next question. How would you recommend splitting the topic between the two partners? Because I know some people recommend this. Ooh, that is so that does kind of go counter to what I spent the first part of the talk talking about, which is that all the topics on the rule sheet are related. So keep in mind that if you're going to split the topic, you might want to have cursory knowledge about what your partner is learning. So for instance, um, if someone takes all the properties, right, which is G, H, and I on the rule sheet, they might also want to know a little bit about the structure of materials. And they might also want to know a little bit about the nanomaterial synthesis and fabrication, because we might ask questions that kind of combine the two. So, not saying don't split it, but you might have to be creative.
Erin, one suggestion, see if this makes sense, is don't think of it as necessarily the topics, but maybe split it along the types of nanomaterials. So maybe somebody like, Erin gets really into the fluids, I get into the nanotubes, and that may be one way to kind of break up the information a little bit, or to break up your studying, right? Because as Erin says,
Yeah.
everything is so connected. It's almost akin to like if I was doing rocks and minerals, right? Like I'm going to worry about the igneous rocks. Erin's going to worry about the metamorphic rocks, and then we split what's left. I'm forgetting now. I'm blanking on what the third type of rock is, but you can. Hopefully
Sedimentary?
yeah, sedimentary. Thank you. That hopefully that gives you kind of an example and an idea.
I think that's a great point. Yeah, I think if I was going to split it, that's a great way of doing it. So maybe don't split it along the topic lines. Take the types of nanomaterials and split it that way. That's a great idea.
All right, everybody. Well, at this point, we've gone a little over time, but I want to thank you guys for hanging in there, and hopefully, you got useful information. Erin, thank you so much for doing this. It's fantastic. I always love sitting in on these things and running these because I always learn some stuff. But at this point, we're going to go ahead and shut it down. You'll get the recordings tomorrow in raw form, and we'll have the final ones up on the our YouTube channel probably early next week. Um, and there's a couple of questions that have popped up in the chat or that I would encourage you to go back in particular, check out Erin's section 3 on managing the labs. I think are going to give you some good tips, and she review that section when you get the recording, because I think that'll tackle some of your stuff. And um, the question quick about I put in there on the chat about looking for questions. You can buy the starter packs, and they came back and said, well, their school isn't purchasing them, guys. Starter packs are $12. Like that's one day. I mean, that's a meal at McDonald's these days. And you can purchase them online at the Science Olympiad store. If obviously, I don't think any of very few of you probably have your own credit card, but your parents can easily purchase them. They do not have to be a school purchase. So that's definitely something to check out. All right, everybody. Well, thank you very much. Please thank Erin for me, and good luck with the rest of your season, and hope to see you at a Science Olympiad event.
All right. Bye, everyone.